Hey everybody, this is the charge repulsion exercise, but now we're at the glass board. You might be wondering where your previous instructors went. They did record the video for the glass board, but they got lost in transit, so I'm here doing it for y'all. And so let's just remember back on what this charge repulsion exercise is. So we have some positively charged particle, could be like a proton or just any positively charged element, and it has some initial velocity, and it approaches another positively charged particle. And in the exercise, you saw that as the particle approached the other positively charged particle, at some point it stopped, and then it turned around and got launched back. And so what we want to know is, what's this distance of separation at this instance? But before we get into it, let's just define things that we do know right now. And so we know that initially our particle has some kinetic energy initial. And as well, there's some potential energy due to the closeness of being with these other positively charged particles. And then over here, we have some kinetic energy final and some potential energy final. And one thing, like if we think about it, it stopped at this point. You saw in the exercise, it had a moment where it stopped, which is what we're looking at, before it turned around. And so that must mean there's no kinetic energy. And so we know that we'll only have potential energy due to these charges being close to each other. And so something about this is that there's a relationship with these energies due to the law of conservation of energy. And so we know that the kinetic energy initial plus the potential energy initial must be equal to the kinetic energy final plus the potential energy final. And as we stated earlier, we're looking at the moment where this particle stops before it turns around, and we know that this term here goes to zero. And something to note too is that the law of conservation of energy, this is a constant. This just how nature works and how life is, this will always stay constant. And so now we have equations that can define these better, so we can see how to calculate them and what they are. And so we know that for kinetic energy initial, it's going to be 1/2 mv initial of our positively charged particle squared. And then we know that for the potential energy, as described in the exercise, is going to be K Q1, which is the charge of this particle, and we said it's positive, and then Q2 of the opposing charge over here, which was also positive, and then some initial separation distance, Ri. And then over here, we can define better on why kinetic energy final is 0. So it would be 1/2 m, but it would be V final squared. And as we said, at some point when what we're looking at, the particle stops moving, and that means that there would be no velocity here at all. And so anything times 0 is 0, so this term goes away, and this value is equal to 0. And then for the final potential energy, similar setup as over here. We have K times the charge of the first particle and the charge of the second one. And then we have some final separation distance. Let me make this F a little better for y'all, but some final separation distance between them. And so this is our setup here. And so now we want to know what this final separation distance is here. How close does this moving particle get to this stationary, not moving, positively charged particle over here? So I'll move to this side of the board, and we'll write out this equation fully over here, and then we'll manipulate it to find our RF. So when we plug this stuff in, we'll get 1/2 I squared plus we get Q1 Q2 over our initial separation distance Ri And we have no kinetic energy, so we don't need to write in the term 0. So we just write in what the final potential energy is. V2 over some final RF. Alright, so how we're going to approach this to solve it is we want to move RF to be on top. We don't want it in the denominator. We want to move it up. And so what we do is we'll multiply both sides by RF. So we'll put parentheses here because remember when we multiply we need to give it to all terms. So we'll do that so we don't forget. And then what happens here, this cancels out. And then this would get distributed over. And so right now we currently now have RF where we wanted the numerator on top, but now we want to get rid of this big term here. So something else we can do is we can divide the whole thing over by this term. So we get VI squared. And I'll rewrite this. I know it's looking a little ugly right now, but we'll rewrite it so it'll be cleared for y'all. This 1/2 MVI squared K Q1 Q2 RF. Alright. So now when we do that, we have the benefit now, because these terms are the same, we can cut them out. And now let's write down what the final formula will be so we can figure out what the separation distance is at the end. And we get K Q1 Q2, and RF's canceled, so it's not in this side, it's over here as we wanted. And now we got 1/2 MVI squared plus K Q1 Q2. Whoops, this should be RI. This happens, you guys. Making mistakes in math happens all the time. So you always got to double check. It's a common mistake. It can happen to anybody, even me, a grad student. You know, that's perfectly fine. You know, catching these mistakes, that's a big part of this whole experience. Alright, so now we got our final formula for calculating that final separation distance, RF. And so now we want to go back into our code and look at what these values are that were put in. So when you look back at your code, you should have these values I'm about to write down as such. So I'll start here. So we know that the K value is 10 to the 5. We know that, as I've been stating, these are both positively charged particles. Singly, you know, they lost an electron or they were just a proton. So they just got, you know, a charge of 1. And then we had some initial separation distance between this and this particle of 500. And then it had an initial velocity of 50. And so we have all the values necessary to solve for our separation distance. If you plug these into a calculator, you know, you plug in your Q1 and your Q2s where they need to go respectively. Oh, and the mass. Almost forgot the mass. Can't forget the mass. Sorry about that. That's 1. Alright, so we figured out what our final separation distance will be. We figured out the formula. And these are the initial values that we gave into the program. And before we plug in these values and get the separation distance, I just want to make a comment about the units that we're using in some of these. These aren't SI units, which is typically what I use. So for charges, that would be like 1.6 times 10 to the too many, basically. And then similarly for K, I'm used to units of N meters squared over coulombs, and here I'm used to kilograms, but here we're using atomic mass units. And so, and over here we're using elementary charges. And the beauty in that is it makes things a lot cleaner, and it, you know, we don't want you to get lost in the numbers of things. All you really need to know is just, this is a positively charged particle. This has a mass of 1, and it's still like the same physics going on. We're still being true to the units. It's just we switched to different units to make the math a lot easier and also easier on the eyes to read. And so now that we got that, we could plug it in into what the final separation value equation is. And I use the calculator, or use whatever you got. I don't want to use my big brain right now. And so when I plugged it in, I got that the final separation distance was 68.9655. And one thing to know here, that this is the true value. Like, this is all based on physics. This is based on the law of conservation of energy, and all these formulas are true. And so this value is what we would expect in real life. This is, we're just going to write true right here. And if you look back into the program that we made, or that you made, you see that you got 68.94. This is what you observed. This is what our estimation was given the setup of our program. And these programs, they're never perfect. This is just to get, to be able to visualize it. And so it would make sense that the calculation of the computer might not get it close. This is really close, but you could never really trust the computer. That's why we go back to the whiteboard, so you can see okay, this does make sense. You shouldn't just trust this value when you run your program. That's why we do this here. And so let's get into kind of what the error is. And here I'll write this is observed. I'm gonna do just OBS for sure. And so when we want to calculate the error, it's always the true value minus the observed value, which is from your code, from your run of the code you made, over the true value. And this gets you the amount of error there is in the system. And if you want to get percent error, you just throw in 100 out front, and you could throw a percent sign on. And so when we plug in these values here, I'll just throw them in for y'all. I'll throw percent parentheses here, actually. Be consistent. 6.965 minus 68.94 over the true value, which is 60. Let me rewrite that. 68.9655. When you plug this in, I'm around, you'll get about 0.04%. Now, honestly, I went over the program. I run simulations myself, and I've never gotten nowhere near a 0.04%. That's kind of it's a pretty wild thing to happen for this simple program that y'all made. But we double checked everything. We looked at the honest physics. We figured out the true value, and so it's a pretty good simple program. Even with these unit conversions that we had done, we know this is true. So yeah, this is a great result.